doubts related to the remaining part of base and min-max estimation, or the starting portion of asymptotically efficient estimators, you may discuss those doubts today. Yes, any doubts you have? Did you go through the lectures or the notes? Yes.
Sir, in the part where we have derived the risk function of A, formulation of testing and decision problem. So in
Okay.
that part,
Yeah.
I cannot understand how we have converted the expectation to the probability.
Let me see that testing problem as a decision problem, right?
Yes, sir.
So let me see. Can you see the notes?
Yes, sir.
Okay. This should be towards the end, I guess. I don't know whether it is there in lecture notes or not. Let me still check it.
Sir, sorry to interrupt. Am I audible, sir?
Yeah, yeah.
Sir, some of my friends are in the waiting room.
Yeah, so this is the thing. So if you look at the classical testing problem, what you have is you have a random sample x1, x2, xn with a PDF f, which I know could be either f0 or f1. So it has only just two possible choices, f0 or f1. With respect to a dominating measure, I have written down it in a measure theoretic language so that it covers both discrete case as well as continuous case. When dominating measure is the Lebesgue measure, it means your f is continuous. When dominating measure is the counting measure, it means f is discrete. So you don't get into that complexity, which means f is either discrete or continuous. And you are interested in testing whether f is same as f0, where f0 is totally specified. Against that, f is same as f1. Right? So for example, it could be normal 0, 1. F0 could be a PDF of normal 0, 1. and F1 could be a PDF of normal 0, 2. So both are completely specified. There is nothing unknown. So you have to test F0 against F1. So how does the Neyman Pearson lemma says? It looks at, you look at the density under F0, look at the density F1, and accept H naught if F0 xi upon F1 xi is greater than K. Accept H1 if this is less than K, and accept H naught with probability gamma if this is equal to K. Now this is equal to K if you require this, if you remember, this was required because in the discrete case, sometimes to achieve the given level of significance, you need equal to K. Otherwise, in discrete distribution, they may be jump, and equal to K probability will never be achieved, right? So what I do is, I try to formulate this problem as a decision problem. So what is happening over here? You know F is either F0 or F is F1, and you have to decide whether F is F0 or F is same as F1 based on the observation X. So that means based on an observation X, you have to take two possible actions. One action is accepting F0, one is accepting F1. You can call those actions as A0 and A1. So my whole parameter space is F0 and F1. So this is a class of all distributions which I can call as 0 and 1. So 0 means my actual density is F0. 1 means my actual density is F1. And I can denote action space by A0 and A1, where A0 means I take the action that F0 is true, and A1 is the action that I take the action that F1 is true, based on the observation. So that is what I have written down. AI is that accept HI. There is a loss function because whatever action you take, there would be a loss associated with it. Loss is a function of L theta A. Theta is the true state of nature, and A is the action which you take. What are the two state of nature over here? True state of nature is that your density is either F0 or density is either F1. So in place of theta, you have LF, where F is F0 or F1. What are the actions you can take? That means either A0 is true, that means F0 is true, or you take the action A1, that F1 is true. What are the loss function? LF0 A0. LF0 A0 means you take the action that F0 is true, where actually F0 is true. So that means you are making a correct action. In such a case, loss is 0. What is this? This means you take the action A1, that means you take the action that F1 is true, whereas actually F0 is true. So there is incorrect decision. Incorrect decision may be denoted by some positive quantity, which is B. Similarly, LF1 A0, that means you take action A0, that means you are saying that F0 is the true PDF, where actually F1 is the true PDF. So this also corresponds to the incorrect decision. So there may be a loss C, which may be different from B, right? So asymmetric loss. And then LA1 F1 means you are again making a correct decision. That means you're taking action that A1 is true, which is saying that F1 is the true PDF, where actually F1 is the true PDF, making the action. What is a decision rule? Decision rule for every X does a randomization on the action space. Now here action space has only two elements, A0 and A1. So my decision rule for every X is a discrete probability distribution. That means it takes action A1 with certain probability, it takes action A0 with certain probability. So that is what I have said. Delta can be a map from chi cross A. Chi is a sample space, A is action space to 0, 1, such that delta of A0 given X is nothing but probability of taking action A0 given X equal to X, and delta of A1 given X is same as probability of taking action A1 given X equal to X. Now, since it is a probability distribution on an action space which has only two elements, A0 and A1, so delta A1 given X for any X has to be same as 1 minus delta of A0 given X, right? So that means your Yx is a random variable which takes two values, A0 with probability delta A0 given X, and Yx is A1 with probability delta of A1 given X. That is what it means. Now note that any decision rule has two components for a given X, delta A0 and delta A1, and they are related by 1 minus of another. 1 minus delta of A0. So I can as well denote a decision rule only by delta of x, where delta x is nothing but delta of A1 given x. That is what I've said. I can denote delta A1 given x by just delta x. Then delta A0 given x is nothing but 1 minus delta x, because there are only two possible x's. So this suggests that because any decision rule will have two components, delta A1 given x and delta A0 given x, and both the components are determined only by delta x, so I can represent any decision rule by delta x with the interpretation that delta x is the probability of taking action A1 when x is observed. So 1 minus delta x would be probability of taking action A0 given x. Right? So any decision rule can be represented by just delta x. Now this is done to make our notation simple, so that all the time I don't have to consider delta of A1 given x and delta of A0 given x. I can just have delta of x, which is nothing but delta of A1 given x, and I can represent delta of A0 given x by just 1 minus delta of x. So that is what it says. Thus, a decision rule delta can be simply denoted by a function from sample space to 0, 1. In general, a decision rule is a function from chi cross A to 0, 1. But here, since A contains only two elements, A0 and A1, so delta of A1 given x is 1 minus delta of A0 given x. So A1 is already determined by A0, so I can forget about this A, and I can write down my delta as map from chi to 0, 1, where delta x is probability of taking action A1 given x equal to x. So probability of taking action A0 given x equal to x will be nothing but 1 minus delta x. Is that okay? Now, what is expected value of F0 delta x? Right? What was so I'm taking expected value of this probability, right? Now, if we take expected value of this probability, what is happening? By Bayes theorem. By Bayes theorem, what would be expected value of delta x? Here x was fixed. Now taking averaging over x. So this would give you unconditional probability of taking action A1 given when sampling from F0. Because what does Bayes theorem says? If I have to take expected value of this, what does it mean? Let us say in the discrete case, it would be summation over delta x, then P F0x. By theorem of total probability, what is that? Because x, you have summed over all possible values of x. So that means it becomes now unconditional probability. Is that okay? So that is why this is same as unconditional probability of taking
Yes,
x A1 when sampling from F0. It is by theorem of total probability. Because what does theorem of total probability says? For example, let us look at when you are finding a marginal distribution. What do? You integrate out the unwanted variable in the joint distribution.
yes, sir.
But joint distribution is same as conditional multiplied by marginal of x, which is nothing but a Bayes theorem, which is nothing but theorem of total probability. That probability of A given B, then multiplied by probability of B, and then you're integrating over probability of B, whatever is the possible values of probability of B is. Right? So that is what you're doing. Probability of taking action given, first you write down the conditional probability. So these are conditional probability, and then you sum it over all possible values of x. Is that okay? Is that clear?
Sir, but what are the values that delta x can take? That is, we are taking expectation, so it should be summation over x.
It should be summation or integral depending on F0 is continuous or discrete.
Yes, sir.
Yeah.
Yes, sir. So for the discrete case, summation over delta x into probability when
Summation over delta x into F0x.
F0x. Yes, sir.
Is that okay? So delta 0x is a probability of A given x, probability of AI given x.
Oh, okay, sir. So it is becoming probability a given x into probability x equal to x.
What is the probability of x under F0?
Oh, yes, sir. Then the total probability and the,
Right. That is how you are. Is that okay?
yes, sir. Yes, sir. Now
And
it's
that is how you get the marginal also now. Marginal, how do you get? You apply the theorem of total probability.
yes, sir.
Joint you consider and then integrate over all possible values of unwanted variable. Is that okay? Which is same
Yes,
as
sir.
consider joint as conditional, multiplied by marginal, and integrate out all unwanted variable. Is that okay?
Yes, sir. Yes.
Okay. Any other doubt? Would you like to discuss any other doubt you have from the notes? How was the exam?
Average.
Huh? Average.
Average. Yes.
It was lengthy, right?
Yes, sir.
It was made lengthy purposefully so that you don't get a time to collaborate. But still, some of you collaborated, I can see from the answer scripts. So there were some exchanges between you. Yes, any other doubts you want to discuss?
Sir, in the proof of the theorem that an admissible estimator with constant risk is minimax. So, in the second part, where you have proved the unique minimax part,
Right.
that part, where does the strict inequality come?
If the loss function is strictly convex, then you know that in the Jensen's inequality, there is a strict inequality, right?
So the strict inequality is coming from L theta alpha A1 plus 1 minus alpha A2 is strictly less than alpha.
Right, right, because L is strictly convex.
Yes, sir. But in the video lecture, you have said that delta naught and delta one are different. The strict inequality is coming from that part. So I
That
cannot
is also there, na? Because you
that part
see,
I cannot understand.
yeah, because deltas, let us look at. Because in the Jensen's inequality, if your loss function is strictly convex, under what condition you can have an equality? Only when those points are same,
Yes, sir.
right? Here delta 0 and delta 1 are not same. So that is why there is a strict inequality. You want me to go over those video lecture?
Sir, explain that part delta naught and delta one and
So you
same.
want me to go to the notes or video lecture?
Sir, notes is fine.
Notes is fine. Okay, let me see. This is the one, right? And an admissible distributor with constant
Yes, sir.
is minimus. If theta is strictly convex, then an admissible distributor with constant is uniqueness. So first I prove that suppose delta naught is an admissible and it has a constant risk, then I'll show that it is minimax, right? So on contrary, I suppose that delta naught is not minimax. What does that mean? That means there exists an estimator whose supremum risk is smaller than the supremum risk of delta naught. So that means there exists a delta star belonging to D whose supremum risk, which is supremum theta belonging to theta r delta star theta, is less than the supremum risk of this constant estimator. Supremum theta belonging to theta r delta naught theta. But r delta naught theta is constant, so supremum would be C only. Now supremum is less than C. What does that mean? That means each point is less than C because supremum is always bigger than or equal to individual point. So that means each point risk is less than C, which is same as R delta naught for every theta belonging to theta. What does that mean? There is the estimated delta star whose risk is always smaller than the risk of delta naught for every theta. That means delta naught is inadmissible. That means you have found an estimator whose risk is always smaller than that of delta naught. That means delta naught is inadmissible by the definition of inadmissibility, which means delta naught is. But this is a contradiction because you are given delta naught to be admissible, so this is a contradiction. Okay. Now suppose that a loss function is strictly convex, right? And I'm saying certainly this would be. I've already proved that any admissible estimator with constant risk is constant. is admissible, is minimax. Now let delta be any other estimator which is minimax, right? I have to show that such an estimator is unique minimax. Now to show that it is not unique minimax, what do you have to show? That means there is some other estimator. So that means there delta star be any other estimator whose supremum risk is same as supremum of r delta naught theta, which has a constant risk, right? And delta naught is given to be admissible. And delta star is equal to delta naught does not hold almost surely, because I'm saying delta star is any other estimator, right? Because so what I do is I construct another estimator using delta star and delta naught as delta double star, which is delta star plus delta naught by 2. Right? Then R delta star theta would be expected value of L theta delta star plus delta naught by 2. Now, if you look at this point, L is given to be strictly convex. What does that mean? And delta star and delta naught are different. So this would be less than or equal to half times L theta delta star plus half times L theta delta naught. Because if they were same, then this quantity would be the same. No? You see, if L is strictly convex, H is strictly convex, then H of alpha x plus 1 minus alpha y would be strictly less than alpha times Hx plus 1 minus alpha hy, provided x is not equal to y. Because f is equal to y, both the sides you will have equality, right? And that is why it is strictly less than, right? Now this is less than, and delta star and delta naught with probability, positive probability, they are different, right? So that is why when you take the expectation that inequality is preserved. So there was an inequality preserved here in L. Why it is inequality is preserving over less than A? Because the probability that delta star and delta naught are different, that probability is positive for every theta. That is why this is preserved under expectation also. Is that okay?
Yes, sir.
Okay. Any other doubt? Yes, anybody else? Anybody wishes to ask a doubt?
Hello, sir.
Yeah,
Sir, can you explain that diagram in the Bayes rule?
Bayes rule. Yeah. So you see, the whole the whole idea is that what we said is if you look at a risk function of a 2-action decision problem. So like a testing problem, there are 2 possible actions. The risk of any 2-action decision problem is a convex set, right? It would be a convex set in R2, 2-dimensional equilibrium space, because there are 2 state of the nature also, only F0 and F1, right? And then I mentioned, I did not prove it explicitly, that given any convex set in R2, you can always construct a decision problem for which this is a risk set. Is that okay? All right? So let us yeah. So there are 2 states of nature here. Can you see the screen?
No, sir.
Oh, you haven't seen the screen. I have to share the screen. This is... Can you see now?
Yes, sir.
So yeah, so let us look at two states of nature 0 and 1, and two actions 0 and 1, right? A decision rule delta is a map from chi cross A to 0, 1. And I have said in a two action decision problem, there is no need to consider delta A0 given x and delta A1 given x. Delta A1 given x itself I can denote by delta x, which is probability of taking action A1, or 1 given x equal to x. Then 1 minus delta x would be the probability of taking the remaining action, which is the action 0. So 1 minus, which is same as probability of taking action given x equal to x. Suppose L theta is the loss function. What are the possible values of theta? Possible values of theta are in
0
omega,
and
which are 0 and 1. What are the possible values of A's? A's are also 0 and
0
1.
and 1.
I just represented. So first I have to look at what is the average loss when randomization is on the action space. Right? So that means randomization done by delta x. What would be this? Delta x is the probability of taking action A1. And probability of taking action A0 is 1 minus delta x. So L theta taking action 0 multiplied by corresponding probability 1 minus delta x plus L theta 1 multiplied by the corresponding probability of taking action 1, which is delta x. So this is the average loss when randomization is done at the level of delta. Right? Now for a given decision rule delta, I define V delta as R delta 0 and R delta 1. Right? Because this function is R delta theta. Theta here can take only two values in 0 and 1. So for any decision rule, my classical risk when I take the average risk of L star theta delta x with respect to probability distribution of x, which could be F0 or F1, I get 2 points. R delta 0 when I'm taking integral respect to F0, and it will be R delta 1 when I'm taking integral respect to F1. So there are only 2 points, R delta 0 and R delta 1. So you have a risk only at 2 points, R delta 0 at the state of nature 0 and R delta at the state of nature 1. So that means my any risk function can be represented by a point in R2, because R delta 0 and R delta 2 only 2 points. So I define for a decision rule delta V delta as R delta 0 and R delta 1 as a point in R2. So what is happening? For any decision rule delta, its risk function can be represented by a point in R2. So as I vary decision rule delta, I get a variety of points in R2. And each point in R2 corresponds to a risk of a decision rule. So S is V delta, which is delta belonging to D, which is a risk set. What is a risk set? It is a risk of any decision rule. So it is a set as you vary delta, right? And V delta is represented by R delta 0 and R delta 1. So for any decision rule, you have R delta 0 and R delta 1. Now I vary this delta and I've got a risk set. The first result which we do is the risk set S is a convex set. Right? That is a proof which I have given over here. The idea is very simple, because if you look at any two probability distributions, their convex combination is again a probability distribution. For example, if alpha is a density, sorry, F is a density, F0 is a density, F1 is density, then alpha times F0 and 1 minus alpha times F1 is also a density. So that means if I look at any 2 points in risk set, they would correspond to the risk of two different decision rules, delta 1 and delta 2. So I look at 2 points in S. Since they are point in S, they would be the risk of some decision rules. I'm saying suppose X is the risk of decision rule delta 1 and Y is the risk of decision rule delta. So I took any 2 point in S. And then I look at any point B, beta. What I have to show that beta X plus 1 minus beta Y also belongs to the risk set S. The only thing is that I have to show that beta X plus 1 minus beta Y belongs to the risk set S, what I need to show that beta X plus 1 minus beta Y is also a risk of some decision rule. And then I show that, yeah, it is a risk of a decision rule, which is nothing but beta times delta 1 plus 1 minus beta times delta 2. That is what I've done. I consider a new decision rule based on delta 1 and delta 2. Delta 1 and delta 2 are given decision rules. Based on that, I constructed decision rule beta times delta 1 plus beta 1 minus beta times delta 2. Now, this is certainly a decision rule. Why? Because if delta 1 is between 0 to 1, delta 2 is between 0 to 1, their convex combination will also be between 0 to 1. So delta beta is a decision rule which for a given beta takes xn a1 with probability beta times delta 1x plus 1 minus beta times delta 2x. Okay. Then I consider L star respect to delta bx, which is 1 minus delta beta, which is a probability of taking xn a0 times L theta a0, plus delta bx, which is same delta beta x, which is probability of taking xn a1 times L theta a1. So this is based on a randomization at the level of decision rule, delta beta. But delta beta is same as beta delta 1 plus 1 minus beta delta 2. So which is same as minus beta delta 1 minus 1 minus beta delta 2 x L theta a0. Delta beta x, which is beta delta 1 plus 1 minus beta delta 2x L theta a. So I add and subtract here beta. So it can be written as 1 minus beta plus beta times 1 minus delta 1x is becomes, and 1 minus delta 2 was already over here. So beta times 1 minus delta 1x minus 1 minus beta delta 2x L theta is 0 plus beta delta 1x plus 1 minus beta delta 2x L theta a. So beta delta 1 minus delta 1x plus 1 minus beta delta 2x times L theta is 0, right? Because it becomes 1 minus beta L delta 2 times beta delta 1x plus 1 minus beta delta 2x L theta a. What does that become? Yeah, beta becomes common. So 1 minus delta 1x L theta a 0 plus delta 1x L theta delta a1 plus 1 minus beta times 1 minus delta 2 L theta a 0 plus L theta a1 delta 2x, right? What is this quantity? A0, this is a probability of taking xn a0 based on decision rule delta 1. A1, this is a probability of taking xn using decision rule delta 1. So it is the average loss of decision rule delta 1. So that is L star theta delta 1x. Similarly, this is nothing but average loss of decision rule delta 2. So 1 minus beta L star delta 2x. So what I see is R delta beta x, which would be expected value of this quantity with respect to probability distribution of x, is nothing but beta times expected value of this quantity, which is nothing but risk of delta 1 at the point theta. So R delta 1 theta plus 1 minus beta expected value of this, which is nothing but risk of delta 2 at the point theta. So this is what it is. So what does R delta beta, what is the risk of delta beta? It is nothing but convex combination of risk of delta 1 and 1 minus delta 2. So what does that mean? That means beta, this was point x, this was point b, y. So beta x plus 1 minus beta y is a risk of some decision rule. If it is a risk of some decision rule, that means it belongs to a risk set. So this turns out to be a convex set. So risk set in a 2xn problem would always be a convex set. And conversely, one can show that if you are given any convex set in R2, it can be considered as the risk set of some decision problem. Right? So I'm trying to see, now if it is in R2, that means any point in R2 can be considered as a risk of any decision rule, which has two actions and two state of nature. So I see what would be the nature of base rules, geometrically where base rules would be, right? Now, base rule here, I need a prior distribution on state of nature. State of nature is 0 or 1. So I need to have a probability distribution on state of nature. That is, what is the probability of 0 being true, theta being 0 is true, and what is the probability of theta is equal to 1 being true. So suppose probability of theta is equal to 0 is p, then probability of theta is equal to 1 would be 1 minus p, right? Because it has to be prior distribution, has to be a proper probability distribution. So what would be my R delta p? R delta P would be average risk of R delta theta. R delta theta has two components, R delta 0 and R delta 1. So this is R delta 0. Then what is the probability that theta is equal to 0? Is P. So P times R delta 0. Theta is equal to 1. 1 minus P, R delta 1. Right? So this is the base risk. So what is the base risk? You go to the risk set and consider the point of the type P times R delta 0 plus 1 minus P times R delta 1, which is same as P times X plus 1 minus P1. What is XY point? XY point is R delta 0 and R delta 1, which is a XY point is a point in the risk set. Right? R delta 0 and R delta 1. So I have to minimize Px plus 1 minus Py for various points X and Y is in the risk set. Right? Is that okay? Because point XY is the risk of decision rule delta.
Yes.
Right? So I have to minimize Px plus 1 minus Py. So I consider, suppose my S is a risk set. So I've considered, suppose my decision problem is such that my risk set looks like this, right? So all these are, so what are the various points inside this risk set? They correspond to the risk of some decision rule, right? Any point over here would correspond to risk of some decision rule. So I'm trying to look at what is the line Px plus 1 minus Py. I have to minimize this. So I consider the line Px plus 1 minus Py is equal to C. Right? Px equal to 1 minus Py is equal to C would be a line of this type with a positive slope. Sorry, it would be a decreasing, right? Because these are decreasing. If you write down this as a function of y, so it has a negative slope. Y is minus P upon 1 minus Px. So negative slope, so that is a decreasing function of this. And it has an intercept as at C is equal to x at y is 0, that means x is C by P. So it has an intercept at C by P. When y is 0, when x is equal to 0, y is C upon 1 minus P, so it is an intercept over here. So this is a line. But this C would keep varying, because why C would keep varying? P is fixed because my prior distribution is fixed. C would keep varying because point X and Y would keep varying. The only thing is this line I cannot consider because this line doesn't come over here. There is no X and Y which corresponds to over here. So what I try to do is I keep moving this line up and I try to see for which point this line just touches over here. Because that would give me the minimum this thing. So LC is collection of all those XY such that Px plus Qy is equal to C is a line with negative slope. Now as C increases, the line LC moves up. For minimizing R delta pi P fixed, we want to pick the smallest C such that LC intersection S just touches over here, right? Because I have to minimize this C. Now I cannot consider this C in this case over here because there is no X and Y which corresponds to this C, because X and Y have to belong to the risk set. So I have to look at the minimum intercept C by P. So what I do is I keep moving this C up and try to see, and I keep moving until a point I get a point XY in the risk set C. The moment I have got it over here, so I keep on moving this line. Suppose this moves line like this, and this touches over here. And here I have gotten a point which touches over here, which could be a tangent kind of a point over here. So then this point corresponds to the risk set of a Bayes rule. So this point would correspond to the risk of a Bayes rule. So I have identified what is the Bayes rule over. Is that okay?
Yes.
So for example, in this case, now the slope depends on what P is. So as you keep varying B, for a fixed P, this may be a Bayes rule. You change the P, the slope of this line may keep changing. You may get some other as a Bayes rule. So all these points, by changing P, you might get as a Bayes rule. So all Bayes rules here looks like correspond to the lower boundary of this set. Is that okay?
Yes, sir.
Now in this case, now this might, and where are the admissible rules in this risk set?
Sir, they are also will be on the lower boundary.
Lower boundary, because any point
Yes, sir.
which is not on the lower point boundary gets beaten by drawing a projection of it in the lower boundary point,
Yes, sir.
right? So now this may give a rise to a question that any Bayes rule looks like Bayes rules and admissible rules are same, right? This might be impressive. So if you have to argue heuristically, no, the set of Bayes rules may not be same as a set of admissible rules. You say, let us look at this kind of a set. Now, this is a convex function, a convex set in R2. Because what is the definition of convex set? You take any 2 points, join the line segment between them, that should be totally inside it. So I look at the risk side inside it. All these points may correspond to the Bayes rule because your line, if you're chosen P such that your line is parallel to the x-axis. Parallel to the x-axis means whole weight is given to R delta 0. So Bayes risk become P is equal to 1 for R delta 0. So R delta 0 is, that means probability theta is equal to 0 is 1. And probability theta is equal to 1 is 0. That is what I am saying. Probability theta is equal to 1 is 1 and probability theta is equal to 0 is 0. So suppose my prior is this. Then what is my Bayes risk? My Bayes risk is P times R delta 1. So 1 times R delta 1 plus 0 times R delta 0. So that will not come, it will be R delta 1. So my Bayes risk is only R delta 1. So these are these points. So what will be the Bayes rules? I keep on moving parallel to the x-axis, then all these points would be Bayes rules. But they are not corresponding to, they all are not admissible. The only admissible point is this. Because if I take any point over here, that is inadmissible. Why? Because that gets beaten by this estimator. Because for this estimator, R delta 0 is smaller than the one over here.
Yes, sir.
And Y is fixed. So here R delta 0 for this point is always smaller than, for this point is always less than or equal to R delta of the point over here with the strict inequality for theta is equal to 0. So all these rules are although Bayes rules, but they are not admissible. So saying that the set of Bayes rules is same as set of admissible rules may not be correct. Is that okay?
Yes, sir.
So that is how geometrically various things are being taken. So for example, if you have to look at how does a minimax rule looks like. If your risk set is like this, what is a minimax rule? Which minimizes the maximum risk. So to see the maximum risk, what I do is I draw the line x equal to y. For all the points over here, what is the maximum risk? It is the y-axis, right? No, sorry, x-axis, because here x is greater than or equal to y. Right? So x is greater than or equal to. For all the points over here, y is greater than or equal to x. So what is the maximum risk? Y. So for all the points over here, the maximum risk is the x coordinate. For all points over here, the maximum risk is y. So where it is minimum? The minimum would be over here. The maximum risk would be minimum over here. At the point x equal to y. Because if you look at any point over here, here x is greater than or equal to y. So what is x greater than or equal to y? I have to look at, yeah, any point over here, what is the maximum risk? The x-axis. So all the points over here, the maximum risk is x-axis. And for all points over here, x-axis is minimum for which point? For this point.
Yes, sir. Okay.
If I look at all the points over here, what is the maximum risk?
Y.
Y-axis. For
Yes,
all the
sir.
points over here, what is the minimum y-axis? Again, this point.
Yes, sir.
So whatever may be the point, whether you take a point over here or a point over here, the maximum risk is minimum for this point. So this is the minimax rule. Is that okay?
Yes, sir.
Now look at, suppose your risk set is such that it is only one on one side of the line x equal to y. So here, the maximum risk will always be x-axis for all the estimators. And maximum risk is minimum when? Only at one point, this point. Because here, maximum risk x-axis becomes larger than that this over here. So here the minimax rule is minimum. Sorry, unique. So it is an example where minimax rule is unique.
Unique.
Right? There's only one rule. So this is geometrically I have given various interpretations. Bayes rule may not be minimax. So here, for example, you may always choose P such that your slope is same as the slope of this line. When you move, all these rules may correspond to the Bayes rules. But the minimax rule would be only this point. So a Bayes rule may not be minimax. And note that for this point, Bayes rule has a constant risk. R delta theta 0 is same as R delta theta 1.
1.
Right? Both are same, x-axis and minimax rule may not be unique. I gave this example here. You can consider this as all
Yes,
these
sir.
points are minimax and so on. So that is a geometrical interpretation. Is that clear?
Yes, sir.
So this gives a nice understanding of heuristically understanding various things, right? Whether minimax rule can be unique, whether Bayes rule is always admissible or not, and so on. Yes, any other doubt you have? I think time is getting over. What is the time, exact time? Does anyone has a watch? My watch is
347, sir.
3:47. So I think we are just finishing. So I think I'll take a break. So we'll meet on, I'll try to upload one assignment today. Try to do those assignment problems. No, you still have some assignment problems from the last assignment, right? So try to do those
Yes, sir.
assignment problems. We can discuss those on Friday at 8. I'll try to upload a new assignment on asymptotically efficient estimators, but that you need not do this week. That you may do next week. Right now, this Friday we'll discuss the last assignment only. The remaining problem which could not be covered in the midterm. Is that okay?
Yes, sir.
Okay, sir.
Okay. Bye. I have another meeting. That's why I'm just rushing.
Bye, sir.
Okay. Bye.
Okay, sir. Bye, sir.